All right. First one we can see the answer, but let's just read through. Container 5 Celsius, ice at 0 Celsius. Thermally isolated. What happens to the total internal energy? That has to stay the same, right? That's which law? First law, thermodynamics.
Yeah,
Which,
I mean, I don't know, but yeah.
That's like energy
I
can't be created or destroyed, right? It can't.
Yeah.
It's thermally isolated. It has to stay the same, whether that energy is transferred between them or not. Okay. Cool. Fixed mass, ideal gas is trapped inside a cylinder of constant volume and its temperature is varied, which of the graph shows the temperature of the gas in a pressure of the gas with temperature in degrees Celsius. PV equals nRT, so it should be P and T as a direct relationship, right?
Mm-hmm.
So
A.
Oh wait, A, because it's in degrees Celsius, so it would have to be A.
Wait, what's the difference?
Well, if it were in Kelvin, it would be. If it were in Kelvin, the answer would be C, because this would go straight through. Yeah, it would be 0, 0, because it's PV equals nRT, right?
Oh yeah, okay.
Yeah, but then P is P is proportional to T, but then if T is in Kelvin and we want to go in Celsius, that's Kelvin plus 270. So we have to put so the A is there. These aren't hard. Sometimes you just have to pay attention. This was on our quiz. I don't think there's a need to go over that one, right? Right? Wasn't this one on our quiz?
Mm-hmm.
Yeah. Okay. Which of this shows the total internal energy? U with respect to time t. It's thermally insulated, so it's the same one as.
So A.
Okay. Now what's the definition of the mole? No.
D.
D. Yeah, that's just a definition. And then unified. Okay, so just so we're clear, mole is the amount of a substance that has the same number of particles as the number of atoms and 12 grams of carbon-12, and then the unified atomic mass unit is 1/12 of the mass of a carbon-12 atom.
Yeah.
Okay. Which of the following is assumption made in the kinetic model of a gas? C.
Wait, what's the? I can't see D.
Oh, there you go. C.
Yeah, C.
Yeah. Yep. There's no more forces between. There's no intermolecular forces between gases or between molecules. Then obviously they have to have mass of everything. So equal masses of water at 80 Celsius and paraffin at 20 Celsius are mixed in a container of negligible thermal capacity. The specific heat capacity of water is twice that of paraffin, and what's the final temperature? So we could do this mathematically, but I don't feel like doing that. I feel like you could just do this in your head, right?
So 60?
Wait. They're gonna both reach the same temperature, but water is gonna be more resistant to change, right? So if they both had the same specific heat capacity, it would be 20 plus 80 is, what would it be, 50? It would be 50. But then yeah, because water is more resistant to change, it would be 60. I think it's 60. Yeah. D. Yep. My reasoning was correct, right? Okay.
Mm-hmm.
Kinetic model of ideal gas, which of these is not assumed? We do assume A. We do assume C. I think it's
Wait,
B.
Yeah, it probably is B, but why do you assume C?
I just remember that was one of the bullet points, I think. Because if it takes a long time between collisions.
Oh, okay.
Wasn't that like the whole thing with the diagram, that whole derivation that she showed of?
I don't remember, but yeah, it makes sense.
That'll just mess up, I guess, I don't know, to be honest. I just seem like, I think that's just one of the assumptions. It's like, I don't know if there's a reason behind that. Okay. B, good. Thermal energy is transferred to a solid. These are the three properties. Which of the above properties determine rise in temperature?
B.
I think so, because it's just Q equals MCAT here, right? Yeah. If this were a gas, then it would probably be A. Or no, sorry, not A, but like it would just be 1.
I don't know.
Probably be volume and specific heat capacity. Probably not mass. Yeah, actually, it might even be mass. I don't know. Anyways, Tanya heats 100 grams of a liquid with an electric heater, so it has a constant power up with that. Have we done this one yet or no? This one seems.
I don't think so.
Anyways, after 100 seconds, the rise in temperature is 40 Kelvin. The specific heat capacity is calculated from which of the following? So it's in joules per kilogram Kelvin. So
I think it's A.
Joules. Let me just need.
Because it would be C equals Q over M times delta T in the denominator. And then so Q is 60 times 100.
I see. Over.
And then 100 grams is 0.1 kilograms.
Yes. Okay. Cool. Molar mass is. Oh, this is molar mass. It's not the mole.
Molar mass. Is it C? I don't know.
I think it's the mass of 1 mole. Yeah. Because that's what we say, right? The molar mass of oxygen is 16 grams per mole. It's like the mass of 1 mole. See, yeah. Which of the following is equivalent to a temperature of 350 Kelvin? Celsius is Kelvin plus 273, right? So yeah, D then. Oh. Wait, it's C.
Wait, maybe I did it wrong. I wasn't thinking. I always get confused if it's plus 273 or minus 273. So
Celsius is Kelvin minus 273, right? Because absolute 0 can't be 273 Celsius. Absolute 0 is minus 273. So it's 350 minus 273. Yeah. Okay.
Okay.
Liquid in glass thermometer is in thermal equilibrium with some hot water. The thermometer is left in the water. Water cools. Which of the following is unlikely to be true for the thermometer? So if the thermometer is left in the water, A has to be true, right?
Yeah, and so C has to be true, right?
Yeah, and then B would also have to be true, right? Because if the water's
D is unlikely.
Can't be true. Yeah, or it's unlikely. It could have the same thermal capacity, but we don't. Yeah. Okay. It's so weird that sometimes they say thermal capacity and sometimes they say heat capacity. Yeah.
That's what kind of threw me off. I was like, wait, thermal capacity?
Yeah.
And I realized,
solid of mass M is initially at temperature delta T below its melting point. The solid has specific heat capacity C and specific latent heat of fusion L. How much thermal energy must be transferred for it to melt completely?
D. Those are just the formulas.
Yes, MCAT. Yep. So it just has to. It has to melt. Or okay. Cool. Pure solid is heated until it's at its melting point. While it's melting, the temperature stays the same, so it can't be C or D. The kinetic energy doesn't increase while it's changing because temperature is not changing, so it has to be B. Mean potential energy. Yep. Cool. Which is an assumption. We already talked about that. They just put that question twice. Okay. Container holds 40 grams of argon-40 and 8 grams of helium-4. What's the number of atoms of argon to the number of atoms of helium?
Wait,
I'm a little confused too.
yeah.
What's
wait,
the
wait,
molar
wait.
mass of argon 40? That has 40 grams per mole, right? Argon 40 has 40 grams per mole. Is that right?
Well, no. How would we know that?
Well, because it's argon 40.
Oh,
Wait, that doesn't make sense.
okay.
Wait,
Wait, I don't know.
I don't know.
Maybe? I guess we can assume that it's approximately the same.
Okay, so that means there's 1 mole or 40 grams times
6.0, like 1 mole of atoms, like 1 Avogadro's number of atoms.
Yes. Right? Okay. So wait.
And then,
but it's 1 mole. Right? Oh yeah, 40 grams per mole, and then it's Na, whatever Avogadro's number is. We'll figure that out later.
Yeah.
Avogadro's number per mole. Okay, so that's how many atoms we have. Atoms per mole. Okay.
And then
that's
helium
all
is
divided
8,
by.
so it's just 2 Avogadro's numbers.
So that's 8 grams times. If we wanted to do this, you don't have. You could probably do this in your head.
This seems wrong, but
this seems wrong too. But we'll see where it ends up. So that's 2 Na per mole.
So it would be 1/2.
So yeah, you wouldn't even need to do any of this stuff that we're doing right now. So it's just 1/2. Is it 1/2 A? It is A.
Okay. That's a weird question.
That is a weird question. So molar mass is the like, how do you figure out molar mass from an isotope, like a nuclide?
I think you assume it's approximately the same as the number of nucleons.
Okay. I think that's why we on the periodic we just say, okay, oxygen has 16, right? 16 grams per mole. Because it's weight, or its atomic masses, or I don't even remember what it's called. Whatever it is on the periodic table, that's 16. So we say it's 16.
Yeah.
Okay. I'm fine with that. The following can be determined for a solid substance, which is equal to the internal energy of this solid substance. What?
2 and 3 combined.
Yes, 2 and 3. That's a very weird way of phrasing the question. It seems like usually when it's like these questions, it's like, it's like which of these fall satisfy? It's 2 and 3 combined. Okay. Energy is supplied at a constant rate. Okay. Material begins as a solid. Graph shows the variation of temperature. Oh God, why did they do this?
What do you mean?
They flipped the axes. Oh wait, or no? Is this how they? Is this how they normally do it? Oh, this is how they normally do it. Never mind. The specific heat capacities of the solid, liquid. Okay. So the slope here is in terms of temperature over heat, right?
GL. Okay.
The slope is temperature over heat, right? Time is essentially heat, right? So slope is temperature over heat, and C is equal to Q over M delta T, right? So that means this is essentially some form of, this is proportional to 1 over C. That means higher slope would mean less specific heat capacity. So liquid should have the lowest, yeah. So it should be A or D, and then gas should have the highest, right?
That's solid. Oh wait, no, never mind. Sorry, I'm wrong. It's a gas. Yeah,
it is gas.
I read it wrong.
So D then. I think it's D.
Yeah.
Okay. Yep. D. Mole is defined as, we already talked about this. Elementary entities, blah blah blah. Ideal gas of N molecules is maintained at constant pressure. Volume varies with temperature, T. What is the gradient of the graph?
I don't know what that means.
The slope of the graph. So
Oh,
that's P, if PV equals nRT, and we have a graph, it's like linear, this is what linearization is. Remember, yeah, so that means volume is nR over P times T. So our slope is nR over P.
interesting.
Yeah. Wait, it's C. Hold on. Why is it C?
Oh, yeah, because it's capital N, so it would be NK.
Oh, got it. Yeah, whoops. Okay, just to clarify.
Why is it KB though? Does KB mean something?
Boltzmann constant. That's what Boltzmann constant is, right? Because Boltzmann constant by definition, KB is, in my data book, hold on.
It's like 1.38 or something.
KB is, well, I don't know. I don't need to know what it is. It's just R over NA.
Oh, okay.
So if I have,
Yeah,
N is essentially N over NA, right? So that'll be N times KB over P. Yeah, okay, so it's actually C. Okay, cool. Temperature of 23 Kelvin is equivalent to a temperature of, oh God, it's minus 273?
It's B then.
I think so, yes. A block of iron of mass 10 kilograms and temperature 10 Celsius, part of contact 20 kilograms, 70 Celsius. No energy transfer takes place between, except between the two blocks. Okay, what's the final?
Okay, I was like, it doesn't take place, then what are we doing?
So they're both iron, so same specific heat capacity.
Yeah.
It's just that, but they don't have the same heat capacity because they're different masses.
Yeah.
So if they were the same mass, what would it be? 40?
It would be right in the middle, yeah, 40.
But the 20 kilograms is going to be more resistant to change, right?
Yeah, so it'll be 50.
50? 10 plus 40, 50 plus 20. Yeah, 50. It'll be 50 then. Because 10 plus 40 and 50 plus 20 is 77. That's twice. That works. Good. Okay. What are the units of this ratio? All right, let's see. What a specific heat capacity is in, oh God. Okay, Q equals
joules over kilograms over Kelvin.
Joules over kilogram Kelvin. Yeah. And then latent heat of vapor, specific latent heat.
Joules over kilogram.
So L equals, Q over M. So joules over kilogram. Joules, kilogram. We got 1 over Kelvin, which is Kelvin to the -1.
Why are they lowercase?
Yeah, that should be uppercase. Let's see. Okay. Two objects are in thermal contact. What is determined by the temperatures of the two objects?
Definitely 1.
Definitely 1. The process by which energy, what does that even mean? The process, is that like talking about, I don't think it's 3. That sounds weird. The process by which energy is transferred between the two objects. Yeah, I don't think it's 3. Like that means like conduction or convection or radiation, right? By which energy is transferred. And that doesn't seem like, what does the temperature have to do?
Yeah, I think it might be 2 as well, right?
Okay, the quantity of internal energy stored by each object. Yeah, because temperature is a measure of average kinetic energy, right? So, and kinetic energy is part of. Oh wait, but that's average. Well, if the average kinetic energy increases, then the total kinetic energy will also. Yeah, so I would say 1 and 2. C. Yep. Okay. Process depends on the temperature. Yeah. Okay, like we said. Okay. When 1800 joules of energy supplied to a mass M of liquid in a container, the temperature of the liquid in the container is 10 Kelvin, and the mass of the liquid is doubled to 2M. 3000 joules of energy is required to change the temperature by 10 Kelvin. What is the specific heat capacity in joules per kilogram Kelvin? I think this is just a subtract, like a slope question, like where they have two separate points. We have to just subtract each of them, right? It's joules. The difference in joules is what?
1200.
1200. And then kilograms, the difference in mass is 2m minus m, which is m. The difference in Kelvin is, oh. So I think it's just 1200. Oh, it's not 12.
Well, over 10.
Over 10? Oh, because it's 10 Kelvin?
Yeah.
Okay, so it's 120 over m then.
Wait, I don't really get what you did.
I don't really get what I did either. This just felt like the right thing to do.
What?
I don't know, sometimes my mind works that way. Okay, now let's actually figure out what I did. So I kind of thought of it as like, you know how sometimes when you have graphs and like you get 2 points and to figure out the specific heat capacity, you would take the slope of that, right? That's kind of what I was thinking of doing. So I took y2 minus y1 over x2 minus x.
Okay, I see.
Yeah, except I don't know why the 10 came in all of a sudden. Okay, anyways, let's see. So C equals Q over M delta T, right?
Yeah.
So we know that
the first one would be like 1800 over M times 10, so
times 10.
180.
Oh, it's just 180 over M. So maybe it's just C. Maybe what I did.
But then if you do it with 2, it would be 3000.
3000
over 2m, right?
Over 2m times 10. That's kind of weird.
So 150.
Oh, so then
okay.
It's 120 and then, or 180 and then 150. That's kind of trippy. How does that work? That's really trippy. Like, how does that even make sense? How can it have two separate specific heat capacities?
Yeah, I mean, if you think about it, if the mass is doubled and everything else is the same, then shouldn't the energy required also just be doubled?
Yeah. That's really weird. I just feel like the answer is B. I don't know why.
Okay,
it's you know what I did with like the difference thing, like that just seemed like the right thing to do, because otherwise, like how does that work? If you double the mass, then the energy required should also double. If the temperature stays the same, the temperature difference. Let me see what the answer is. It is B. Think units.
I don't really get it though.
Yeah, let's see what they say. The units of the answer is given as that. Okay, divide energy by temperature and mass, but that's already okay. C was the most popular option, but this is 120 obtained by dividing 1800 by 10 and totally ignoring the container.
Oh, we're assuming there's a container.
I see. That's why you have to do the subtraction, because of the container. It's like, yeah, it's because it's like if you had a graph, right? And you had a y, if it had an extra, right? If it had an extra thing, you can't figure out the specific heat capacity by directly taking one over the other. You have to take the slope.
I see.
Yes. Okay, that now there's a reason for that. It just felt like the right thing to do, but I didn't know why you would do that. Okay. It'd be reasonable to subtract the energies given before by dividing 10, which is, yeah. One candidate can write down the two relevant heat exchange. Yeah, you could have done two separate heat exchange questions, like you know how we do for other stuff, like when ice becomes water, that kind of thing. You could do two separate equations and then subtract them, but that, like they said, that'll take longer. Okay, I'm glad I did this one, because if that were on a quiz or a test, that would be hard to figure out. Under what conditions of density and pressure is a real gas best described by equation for ideal gas?
Oh, we did this one.
Low density, low pressure, right?
Yeah.
Because if it's high density, high pressure, it becomes a liquid or something. We did this one. Yes. It's A. We talked about that one. Specific latent heat of a substance is defined as the energy required at constant temperature to it's specific, right? So change the phase of 1 kilogram. B. How many more do you want to do? You want us to go over the 3 response now?
Yeah, let's switch.
Okay. Okay. Wow. Okay. You just want to start from the top?
Anything's fine.
Or are there like harder ones? Are there ones in here that have to do with both nuclear and
maybe a couple. Oh yeah, the test is on nuclear too. I forgot.
Yeah.
Oh, I forgot. Dang it, I have to study that too.
This is interesting. Let's look at this one. We did the second part as part of the homework, so I don't know if we have to redo that, but oh wait, never mind. We can't do this one because we haven't learned about, well, all this heat exchanger, moderator stuff, that's part of the next unit, so that's not, never mind. Nuclear. Yeah, this is all energy stuff. Nuclear physics, part 1. That's like mechanics. Okay, that's not even. Wow, okay. Okay, do we want to try this one? This is like an A, B, C, D, E, F, G. This is a lot.
Sure.
Okay. Define electric field strength.
Do we have to?
Q equals F over E. Or no, F equals QE. So E equals F over Q. Electric field strength is the force,
Okay.
right? It's a force experienced.
I don't think this would be on the test though.
Probably wouldn't. But I feel like we would need it probably for this, some part here. Or do we just want to start here? Let's just start.
Yeah.
Because this stuff, I think I've forgotten. Protons can be produced by the bombardment of nitrogen-14 nuclei with alpha particles. The nuclear reaction is given below. What's the proton number and nucleon number for nucleus X?
8 protons, 17 nucleons.
17, yep, 17 each. So 8, 7, 8, and 7. 8 and 7. Good. Okay. The following data are available for this reaction. Show that the minimum kinetic energy that the alpha particle must have in order for the reaction to take place is about 0.7 megavolts.
Oh, I just blanked.
I blanked too. You have to multiply by the 931.5, right?
Yeah,
or what is that the number? 931.5?
You have to do, okay, first you do mass defect. Okay, I just forgot everything. Okay, yeah, mass defect.
I forgot everything.
So
rest mass. Wait, do you need mass defect?
Yeah, you do.
Or do you just do that difference thing?
That is mass defect.
Oh. Yeah, that is. Yeah, sorry. The rest mass is 14. Okay, so for the other mass.
It's 0.0007 U. So times
0.0007 U.
Yeah.
And how'd you do that? You did 7 times the proton mass and then 7 times the neutral.
No, I just did rest mass of X nucleus and proton minus nitrogen-14.
Wait, so is that mass defect? I don't think that, like, what's that called?
Is it not mass defect?
Because mass defect is when you figure out the like nitrogen. Yeah, right. That's different, right? Like that's the difference.
Yeah. So what is this called?
I don't know. I think it's just called energy difference. Like that's what it is, right? Isn't that what it is?
But it's not energy. I just do like delta M when I do this.
Oh. Okay. Oh, okay. I write delta E and I just do it all in one step. I write delta E and then I say, this side will be bigger than that side. I totally
said
forgot.
I said I mean, it doesn't matter. You can see afterwards, but I did
okay.
I did
So
products minus reactants.
So 16.9991 plus 1.0073 minus 14.0031 minus 4.0026, and that's in U. So we have to multiply that by 931.5. That's very good. 931.5 over oh wait, well, I do that in the next step essentially. So that's
what's the unit for that again?
So that's mass times c squared times c squared.
Oh right.
So then you have to rewrite. So then now I do this calculation. So what was that calculation? What is this difference here? 0.0. What did you say it was?
0.0007.
0.0007.
Yeah.
Now U itself is defined as 931.5 mega electron volts per c squared. And that multiplies with that c squared there. So c squared cancel, and if you multiply 0.0007 times 931.5, what do you get?
0.65.
0.65 mega electron volts, which is approximately 0.7. I think that's correct. Let's see how they did it. Yep, it gets you to -7 times. Yeah, exactly what we did. Good. Okay. A nucleus of another isotope of the element X decays in D. Okay, here decays with the half-life T half to a nucleus of isotope of fluorine 19. Okay. Isotope. What's isotope?
It's called nuclides. Nuclides with the same number of protons but different number of neutrons.
And half-life is the amount of time
it takes for half of the nuclei in a given radioactive sample to decay.
I think I define it a different way, but it's pretty much the same thing. It's half-life is the amount of time taken by a radioactive sample to decay by half its current amount. Is that right? Or do you have to say half of the nuclei? I think I would probably do. I prefer your definition. That's more precise. I think amount is kind of vague. Same proton number. Yeah. Time for the activity to fall by half a third or half of the radioactive nuclei in the sample. Yeah, that's probably a better definition. Using the axes below, sketch a graph to show how the number of atoms n in a sample of X varies with time t from t equals 0 to 3 half-lives. There are n not atoms in the sample at t equals 0. You kind of just arbitrarily draw that.
I suppose so.
You just label, I guess, how many are there? 1, 2, 3, 4, 5, 6, 7, 8. You could call that n naught, and then call this 1 half-life, and that would go down to here, right? Call that 1 half-life, call that the second half-life, then call that the third half-life. Yeah, that's really weird. So, yeah, okay. Water at a constant pressure boils at constant temperature. Outline in terms of energy of molecules the reason for this. Well, because when it's boiling, you're adding the energy added.
Wait, is it asking why it boils at constant temperature or why constant pressure?
That's a good question. I think it's why it's at constant temperature. I think the constant pressure is just like an assumption.
Okay.
It might have. I don't know. I do that. To me, that's
why it boils at constant temperature.
Well, because the energy the energy
put in is used to break the intermolecular
bonds. Yeah. intermolecular bonds, and all that energy goes towards increase. Hence, all that energy is going towards increasing the potential energy.
Potential energy.
No energy is used to
kinetic energy.
Hence, it boils at constant temperature. I don't know what difference it is. Temperature is a measure of the average. Oh, yeah, you should always say that. Temperature is a measure of average kinetic energy. Energy supplied only increases that temperature. Okay, good. Okay. I think we would get the credit, but it's always good to just define that. An experiment to measure the specific latent heat of vaporization of water. Steam at 100 Celsius is passed into water in an insulated container.
We've done this one.
We've done this one. Yeah. And the homework. Okay. Well, good to review nuclear stuff. Let's see what else is. Yeah, that all that stuff is energy, nuclear reactor, blah, blah, blah. Okay, wait, there was one that I thought I saw. You want to try this one? Want to try this one? Okay. Okay, Rutherford and Royds identified alpha particles. Okay. Write down the missing values of this. Okay, for this equation. 226 grid on 86.2. Alpha particles 4.
222.
222 4. Yep. Okay. Put some pure radium-226 in a closed container or closed cylinder A. Cylinders A is fixed in the center of the larger closed cylinder B. At the start of the experiment, all the air was removed from cylinder B. The alpha particles combined with electrons as they moved through the wall of cylinder A to form helium gas in cylinder B. Okay. The wall of cylinder A is made from glass. Outline why this glass had to be very thin. What? I did not get that. Well, otherwise, how could the alpha particles move through cylinder A, right? Because alpha particles are they interact a lot with matter and they heavily ionize, right? So if that wall wasn't thin, then it would just collide and it would stop right there, right? I think that's probably why it is. A highly ionizing. So you can say highly ionizing or low penetration power or thin glass increases probability of alpha crust glass. Okay. That was just one mark. Okay. Rutherford and Royds expected that many alpha particles to be emitted during the experiment, carried out at a temperature of that. Volume was that. In cylinder A, volume is negligible. Calculate the pressure of the helium gas that was collected in cylinder B. This is a PV equals nRT.
Yeah.
So P equals nRT over V. Which is the same.
I think you use NKT maybe?
Yeah, I would use NKBT here over V. Number of particles is 2.7 times 10 to the 15. KB is what? KB is 1.3 times 10 to the negative 10 to the negative 23. And then the temperature T is what?
18 plus 273.
Which is, I don't have my calculation. Could you do the calculations? Do you have a calculator?
Yeah, I feel like I should be able to do this right now in my head.
I feel like 291.
291.
No, wait,
yeah.
Is that right?
It is. Yeah.
Okay.
I don't know. I'm just not doing this right now. 291, and then the volume is 1.3 times 10 to the negative 5th.
Is the volume in meters cubed?
Yeah.
Okay. Oh yeah, that's that. Okay, so that is 1.3 times 10. Now we really need a calculator. Do you have a calculator in front of you? You put this all in. 2.7 times 10 to the 15 times 1.38 times 10 to the negative 23 times 291 over all of that.
0.834.
Answer is 0.834, so 0.834 pascals. Let's see.
Is that right?
Might be, I don't know. That's correct. Oh, we have to round to two sig figs. I don't think she'd care for now, but that's on the exam.
Okay.
Cool. Okay. They identified the helium gas in cylinder B by observing its emission spectrum outlined with reference to atomic. This is I've forgotten everything from that previous.
I don't know. It goes.
How is an
excited.
emission spectrum formed? Emission is when like it drops, right? It drops energy level. So
it's like black
drop.
black with bars.
Yes. It's the gas is placed. There's a spectrometer, right?
Yeah. A hot gas at low pressure, high pressure.
Low pressure.
Okay.
I think so. I don't know. I do not know. High pressure, because then they're interacting. Wait, no, you would want low pressure, right? Because if it's high pressure, then they would be. We don't want the intermolecular forces to interfere, right? So we want the hot helium gas.
Well, I don't know. Actually, we'll see.
At low pressure. Okay, and then as atoms, I would just say as the electrons de-excite to lower energy levels, they release photons, and those photons create an emission spectrum. That's all I would know what to put. Let's see. Electron atom drops from high energy state to low energy state. Energy. Oh, that's an easy point. They said energy levels are discrete. So the frequency and the energy. Okay, you have to say. So energy levels are discrete.
Yeah.
Yes. Okay. That would be good for me to review tomorrow. The work was first reported in a peer-reviewed. This is like that model question, that we had on our quiz.
Yeah.
Why did they choose to publish their work in this way? Because it increases credibility? I don't know. Like, what?
Yeah, if it's peer-reviewed, more people are checking it. I don't know.
Yeah.
Verifying it.
I would say it's more credible because it's been verified by peers, and then it's I guess more widely read as well because it's more credible. Let's see. Guarantees validity, or they have confidence in the validity, something of that.
This is a dumb type of question.
It is, yeah. I don't know. I feel like this is like a TOK. These are. I feel like this is their way to put TOK.
Yeah.
There's a course called The Nature of Science in IB that you can take. It's like literally TOK inside.
Oh, really?
Yeah. It's like instead of taking physics or biology or ESS, you would take the nature of science.
You can just take the nature. Wow.
Yes. But I feel like that would be harder because it would probably cause you force you to remember science history stuff and probably be way more theoretical. Anyways. Should we try this one? This one's good because it has. We did a little. I don't think we've done this. For thermal.
No.
Okay, all right. Let's start from the beginning and do this. This might actually very well be on our test because it's everything, right? Unified atomic mass unit is
1/12 of the mass of a carbon-12 atom.
Yes, 1/12 of an atom. That's very important. A lot of people put nucleus. So that's wrong. You don't have a lot of things. Yeah, they're very specific. Okay. The mass of a nucleus of Einsteinium 255 is 255.09 U. Calculate the mass in mega electron volts per c squared. You just multiply that by 9.5, right?
Yes.
I don't have my calculator. Sorry. Can you do that?
Sorry.
Yeah, I don't have my calculator.
It is 237,616.
16?
Yeah, I think it would be 5 sig figs, so right?
So yeah.
Or
So
4.
I was
4.
1, 2, 3. No, it's 5, right?
But 931.5, right?
Oh, see, I don't usually take, if it's a conversion factor, I usually don't take those into account. Like ideally,
Okay.
constants they're fundamental, so they're infinitely constant. That's how I mean, I think they would be fine if you went to 5 seconds. I don't think they would. I would probably write that as 2.3762 times 10 to the 1, 2, 3, 4, 5. Mega
yeah.
See what they did. No, they did 4. You're right.
Yeah.
6, 0, 0. So I guess you should take the values of your sig figs or your constants into account. Okay. Now, when particle X collides with a stationary nucleus of calcium-40, nucleus of that and that, okay. Can we figure out what particle X is? I think that would be helpful, even if that's not X. That's 19 plus 1. So
it's
it has zero mass.
Beta. No, I don't know.
That's one mass, or it has a.
Yeah,
is that a proton?
It's a neutron.
Or it's a neutron because it has 0 charge, right? Yes. It's a neutron. Okay. And also, you could probably figure that out if you look at the neutron rest mass and compare that to, like, if you just saw that. Okay. Identify particle X. It's a neutron, like we said. I believe it's yeah, it's a neutron. Good. Suggest why this reaction can occur if the initial kinetic energy of particle X is greater than a minimum value. It has to overcome the energy difference, right?
Sorry, what was the question again?
Suggest why this reaction can only occur if the initial kinetic energy of X is greater than a minimum.
Yeah, it has to overcome the energy difference.
That's how many marks?
Due to the mass defect?
Yeah, I would say it has to overcome the energy difference due to the mass defect.
What does it say?
The rest mass of the products is greater than that of the reactant, so energy must be given to supply this extra mass. I don't know if we would get credit for that.
Close enough.
So it's close. I would think so, but you never know.
That's pretty much what we said in different words.
In different words, yeah. Rest mass of the products is greater than that of the reactants. I feel like they would want you to explicitly say that. So say that.
Yeah, maybe.
Okay. Rest mass of products is greater than the rest mass. Before the reaction occurs, excess kinetic energy. That determines the total combined energy of the potassium nucleus and the proton. So we have to do this plus this times. Okay.
Wait.
The total combined kinetic energy of everything on the right hand. So we have to do 37214.694 plus 939.565, all of that times 930. Wait, that's per megajoule.
Hey, what are you doing?
This is the rest mass in atomic mass units, right?
No.
Then what?
MEV over C squared.
Which is essentially atomic mass.
But do you need to multiply by 931.5 again?
Oh, that's a good question. Oh no, I don't think so. Yeah, you wouldn't multiply by it. Yeah, you're right. That's in. Okay, yeah, because you would just multiply that by C squared, and now it's in mega.
Yeah.
Okay, then you add that to 8.326, and that has to equal 37216.560 plus 938.272 And then there should also be plus the kinetic energy, the extra kinetic energy, right? On this side of the equation.
Why?
Because the mass of the products is going to be bigger than the mass of the reactants, right?
I'm not sure. Wouldn't it be like, wouldn't you first take the mass difference and then subtract that from the kinetic energy of particle X?
Well, okay, so what's the mass difference? You have that?
I'll do it right now.
I think this 8.326 is actually on the other side. Or I don't know. See, this is where I get confused. I think there was a quiz, like on that, there was one quiz, right? I was
0.573.
Okay, so the energy difference is 0.573.
Yeah. So you subtract that from 8.326.
Okay, so what's the equation, like mathematically? It's mass of Earth.
Okay, just do like reactants plus the extra kinetic energy is equal to
Products.
Yeah.
Plus the kinetic energy of
There,
X,
yeah,
right?
yeah.
That's
Well,
weird.
no. Kinetic
Isn't that what
energy
we
of
did
X
though? Or is it? Oh, or is kinetic energy of X on the other side as well?
Yeah. Wait. No. It's kinetic energy of X on the left side, and then kinetic energy is on the right side.
Equals products mass plus kinetic energy products. Yeah. It's just like that.
Yeah.
So how did we?
So the unknown is kinetic energy of products.
Okay.
So you just.
That means it's reactants minus products plus the kinetic energy of X.
Yeah.
But that's reactants minus products is negative, right?
Yeah.
So do you just take the absolute value of that?
No, it's negative, and then you add it to the kinetic energy of particle X.
Oh.
The reason it's negative is because, I mean, like, that's why you need the extra kinetic energy from particle X to overcome that.
Okay, that's right.
So yeah, 8.326 minus 0.573.
Do you always set it up this way? Like all the time?
I mean, when it's a question like this, I mean, I don't know how many questions like this we'll get.
Well, there was just another, I don't think it was like that might be just like one. There was one where I think I messed that up one way or another.
I think I remember what you're talking about, actually.
You remember? Yeah. I can't. Let me see if I can. If not, we'll move on.
It was one that I just solved because like it didn't make sense if you did it the other way. So.
Yeah, that's right. It's this one, yes. It's calculate the binding energy per nucleon for uranium. Okay. So, okay, we did that. Let's do binding energy per nucleon. Oh, it's because it was energy released. The energy released in decay is, you don't put that on the left side. I think energy released, you put that, or energy released, you have to put on the left side. That's what was confusing.
Yeah.
But why do you put energy released on the left side?
I don't remember the exact question, so I can't really answer that. But for this question, I can explain it for this one, but I don't really remember the other one.
Okay, that's okay. Oh, because energy released is negative. Is that why?
Could be.
Yeah, I think it's because energy released. Okay, anyways. Oh, did we even figure this out? What was the answer
Yeah.
that you said?
7.753.
Yeah, that's correct. Okay. Potassium 38 decays with a half-life of 8 minutes.
We're not defining. Yeah, we know it.
Yeah, we talked about that. Sample of potassium 38 has initial activity of 24.
Yeah, you just do half. You know.
24, half of, yeah, okay. Wait, what
I
is
think
that?
we've done this one.
We've done this one, yeah. Determine the activity of the sample after 2 hours. That's just
What was the half-life again?
8 minutes.
Oh, okay. So yeah, you just do.
Do we want to do this one?
It's fine.
That's fine. Let's skip this one. I think we need to get here. Specific latent heat of fusion of a substance is the energy absorbed or released during the phase change of fusion.
Yeah. Okay. So specific latent heat of vaporization is.
And it's fusion here.
It's what?
It's fusion here, not vaporization.
No, there's both.
What?
It says both. Oh no, I wasn't defining it. I was moving on to the next question.
Oh, okay.
I mean, we should probably define it. I just missed that. Yeah.
Oh, okay. Yeah, it's the energy released or absorbed during. Okay, it's the energy released or absorbed by 1 kilogram of a substance during a phase change. In this case, during the phase change of fusion at constant temperature and pressure.
Yeah, from solid to liquid, you might have to.
It could also be liquid to solid, right?
Oh, okay.
From solid to liquid or from okay, so it's the energy released when going from solid to liquid, right? Oh no, it's energy absorbed. The energy absorbed by 1 kilogram of a.
What does it say?
It could be either, I think. Let's see. It's the energy absorbed or released when a unit mass of liquid freezes to become a solid or of solid. Yeah, you could have mentioned either.
Okay.
You just need to say at constant temperature. I would also mention at constant pressure. Okay. Explain in terms of the molecular model the relative magnitude of the water and the specific heat of fusion.
Yeah, so vaporization is higher because it takes more energy to completely separate the molecules, right? In vaporization.
Takes more energy to break those intermolecular bonds.
Yeah.
How many marks is that? It's 5 total.
5 total.
I don't know why that's so many points. Okay. Potential energy change during changes are okay, bonds are weakened. Okay. Greater, more energy required. So this is vaporization. Yeah. Yeah, we talked about that. Okay. Good. Piece of ice is placed into a beaker of water, melts completely. It's the final temperature of water. I don't feel like doing this right now. But it's just let's just set it up and then I don't want to do the math. There's too much.
Sure.
It's so the ice is placed into a beaker of water.
Yeah.
So first, let's deal with the Q ice, right? That's going to be M. First, it's going to melt, right?
Yeah. So latent heat.
But first, it needs to go from its initial temperature.
No, it's already. It's at 0.
Oh, is it already? Oh, it's initially at 0. So never mind. So it's M ice, L ice.
Yeah.
Or L fusion, I guess you could say, right?
Yeah, and then that is equal to
plus. I'm gonna do the whole plus. It's M ice.
But then that wouldn't be Q. Wait. Oh right.
M ice C water now because it's become water.
Yeah.
And delta T, so it's just T in this case because it's the initial temperature 0, right? So then that has to equal Q water, which is M water, C water, and then
80 minus T.
80 minus T.
Yeah, and then you just solve for T.
Okay, and then you said these equal to each other. We're not going to do this math right now. It's just too many numbers. We're going to waste time. You use of, yeah, exactly that. That times that times that.
Yeah.
Exactly what we do. Good. Okie dokes. State two assumptions. First was no energy was lost to the surroundings, right?
Yeah.
And that, or the beaker did not transfer energy to the surroundings. And that, what else?
Yeah.
Is it just those two? That no energy was transferred to the beaker, and then the beaker did not transfer energy to the surroundings. Or I guess you could say the beaker has no heat capacity.
Yeah, I guess that works. I don't know.
I don't know what they're looking for. Yeah. No energy given off
No
to the surroundings and no energy
evaporation?
absorbed here.
Oh.
No evaporation of water. Oh, that's a good point.
Yeah.
Because the evaporation is below them. Right?
Yeah.
Because it's just. Okay, I think what it's just two, right? So the first two that we said were. Cool. Okay, well that was the most. I think that's the most complicated one you'll get. So.
Okay, I think
that's good for today. That's good. For today. Yeah. All right, I'm gonna stop the recording.